Hi and welcome to this new episode of Swift Community. So this time I have with me Thomas. Hello, Thomas.
Hello, Vincent.
So I'm very happy to have Thomas with me today because this episode is going to be an introduction to functional programming. And Thomas is a very good speaker to tell us about this topic because he's the creator of the Bow library on Swift, which enables us to do a lot of cool tricks from the functional paradigm.
Yeah, so today we are going to be talking about functional programming and especially trying to demystify some of the most obscure concepts about this paradigm because, most times when we talk about functional programming, every one of us has a different idea of what it is and how to practice it. So we'll try to discover what it takes to write functional code. So in particular, the outline for today, we're going to be talking about what is functional programming. So what makes our code functional. To do so, we are going to need to define what is a function and what are the properties of a function. And then once we have all these basic building blocks as functions, we will talk about how we can compose them to make larger programs.
So basically, we're going to see like all the basic vocabulary that you need to know in order to then understand like more advanced articles or documentation.
Exactly. So to get this started, we have to ask ourselves, what is functional programming? So if you go to the Wikipedia page or to any other page where you can find a definition of functional programming, you will see that it says something like it's a programming paradigm where we treat computations as the evaluation of mathematical functions, blah, blah, blah. So essentially, the key in functional programming is programming with functions. So we have this construction in Swift. We have a way of describing functions, but not only like free functions like this one we have here. We can treat also methods in classes or structs as functions. And the anatomy of a function in Swift is we use the func keyword, then we give it a name, and then we pass several arguments. And finally, we describe what is the return type, okay? And inside the body of the function, we do some computation. Okay, so we have said that these are the inputs and this is the output type. So one word that we typically find in literature about functional programming is the arity of a function. So what is the arity? The arity is just the number of arguments that a function takes. So this function, this sum function, has arity 3, or we can also say that it is a ternary function. So we can have binary, ternary, quaternary, and so on. So we can ask ourselves right now, are all Swift functions that are proper functions according to functional programming? The answer is no, unfortunately, because functions need to meet 3 properties in order to be considered as functions in the functional programming paradigm. So the first property that they must have is being total. We can say that a total function is a function that provides an output for every possible input, okay? So let's see an example. We have this divide function, and if we only look at its function signature, it takes 2 doubles, x and y, and it says it is going to return a double. However, if we invoke this function with some values, we can see that it crashes. And actually, inspecting the implementation, we can see here that it has a guard statement saying that, well, if you are passing a 0 in the second argument, I'm going to cause a fatal error. And we don't want to have that. The main issue here is that there is nothing in the type signature to tell the compiler, hey, we are going to have a fatal error in this case if you invoke me with certain arguments. So whenever we have such a function like this, we say it is a partial function, okay? So what do you think we can do in order to make this function total?
Well, I would say if you want to still have the same feature, maybe we would need to update the signature in order to make it clear that 0 is not allowed. So I don't know, maybe there is a type or protocol in Swift that says a number that is different than 0.
Okay, that could be one option, saying like this should be a non-negative, non-zero double or something like that, but we don't have such a type, unfortunately. One possibility could be to throw an error, right?
Oh, yes.
So we can declare that this function throws, and here instead of throwing a fatal error, we can create our own division error, for instance. And we make it conform to the error protocol. And here we have to declare one of the cases, and this would be dividend is 0, something like that. And here we instead throw division error dot dividend is 0. Okay, so now with this, we have made the compiler aware that this function may throw errors whenever we have some arguments. But still, this does not make the function total because we are exiting the function through two different branches. One is the return branch, whenever we have a successful value. And another one is at the throw path, okay? The main disadvantage or the main problem here, even though all errors in Swift are checked, is that we can jump several levels out of the context that we are here evaluating at the moment, okay? So we may end up in a completely unrelated part of our program.
Okay,
Good.
so I guess maybe a solution could be like to use something like a result, for instance, or a tuple.
That could be, or if we use a tuple, then we may end up with illegal states that we cannot, we shouldn't represent. So the result type is exactly what we need, because result lets us represent computations that they may potentially fail and still exit through the return branch. So we are going to undo this. So instead of throwing, we are going to return a result of division error. The order of the arguments is reversed. So double or division error. So now we cannot throw, we can return result.failure. And inside we are going to pass the same error value that we were having before. And here we have to return result.success with the actual division that we are performing. So now we have been able to make this function total, and we are always exiting through both, in both cases, through the return branch. And we are even able to explicitly state what is the type of errors that this function is going to be returning.
Yeah, and I think like this solution is very interesting because when we do Swift, sometimes, you know, we see like throws and result as kind of equivalent, but you've just showed us that no, actually result encodes more information than throws because the error, we could say type safe when we use result.
Exactly. So it will force us to deal with both situations, having a successful or a failure value. The failure is going to be typed, and we have a narrow scope of the type of errors that this function is causing. Good. So this is the first property that our functions must have in order to be considered functions in the functional programming paradigm. So the second property that our functions must have is being deterministic. So what does it mean? So it means that whenever we pass a value as an input to a function, the function should be returning always the same output. Okay, this means that we are able to predict what is the output of a function for a given input. Unfortunately, this is not the case in many situations. For instance, whenever we are dealing with randomness or whenever we are dealing with the current date and time. For instance, consider this function. This is a function that takes a prefix and an extension and returns a file name that is based on the current date. Okay, so we are instantiating a date as the now date, and then we convert the file. We create the file name as the prefix dash the current date dot and the extension. What is the problem here? Well, if we try to write a test for this, we cannot predict what is the output of this function. In this case, we can say this function is non-deterministic. Okay, so let's see how we can convert it to a deterministic function. So usually, what we can do in these cases is to extract the sources of indeterminism as parameters to the function. So we can say now date. So now we are able to control this parameter from the outside, and we may take advantage of using default parameters to get the same behavior that we had before, but now we are able to control this and have a predictable behavior for this function. So with this simple change, we are able to convert a non-deterministic function into a deterministic one.
And what's interesting is that we see that in both cases, the pattern is kind of the same, meaning that we are encoding some new information into the function signature. So we see that the signature is going to be, I guess, an important part of the way that we deal with functions.
Exactly, because as much information as we are able to provide the compiler in the function signature, the compiler is going to be able to help us more in compile time. So if the compiler is able to find potential issues in compile time, those are bugs that we are not going to be handling later. So this is the second property. And I said we have 3 properties. So let's see the last one, which is probably the most difficult one to grasp at the beginning. So this property is purity. So what does it mean for a function to be pure? Well, it means that the function only computes its output and performs no side effect. So a function that has this property is said to be pure. A function that performs side effects is said to be impure. Okay. Even sometimes we have use of this term and we call pure functions whenever we have the 3 properties, total, deterministic, and pure, but we can make this distinction. So let's see an example of an impure function. So we have this function that greets you given the name that you are passed here. Okay, so it is going to print a message into the standard output saying hello one plus the provided name. Well, one red flag that we may have is whenever we have a function that returns nothing, this is equivalent to returning void. Okay, so whenever we have a function that returns void, this is a red flag that the function is performing side effects, because we said that the only thing a function can do is compute its output. But if it is not returning anything, so it is essentially not doing anything useful. But most likely, if we are calling it, is because we need the function to do something. So probably what we are doing is running side effects. Good. So if we invoke this function with the argument Swift community, we are going to see a message printed in the standard output as hello one Swift community. Good. So we have said that we are not able to run side effects in our functions. So how can we make something useful if we are not able to run side effects? Because in the end, pretty much everything we do in our applications is running side effects, like updating the user interface,
yes,
performing a network call, logging information, saving things to a database, and so on. So what do you think?
So I guess like we could try and maybe so. I mean, I have the code a little bit below, so maybe I'm reading it a little bit, but I guess the idea would be to encapsulate the side effect somehow and like try and delay its execution like as lately as possible, you know, putting it like at the edge of the program, we could say.
Exactly. So we can encapsulate our side effects and make them as data that we can manipulate later. And at some point in the edge of our program, we are going to have an impure layer, but we can try to make this impure layer as thin as possible. So we have a very big pure core that we can work functionally. And then at the edge of our world, we run the side effects and we let all the impure things happen. So one way of doing this is using the Combine framework that Apple has provided us. So we can use the Future publisher. And for those of you who are still not familiar with Combine, Future is a publisher that lets us work with values that we probably don't have at the moment, but we will have at some point later in the future. So we can create a future by passing a closure where we receive this function promise and that we have to use to signal the completion of the future. So in this case, we are running our side effects, printing a message to the standard output. And right after that, we signal the future finishes successfully with the void value. Okay, and we are calling erase to any publisher. Good. So this may seem like a good idea, but if we actually run this new version of our greeting function, we will see that it behaves exactly like the previous one. It runs the side effects just in the moment we call this function. And why is that? The problem is that Future is an eagerly evaluated publisher. This means that in the moment we create it, it starts running the side effects. And so this is not what we want.
So it starts running even if no one is listening, basically.
Exactly. It starts running the moment we create it. So even if no one is listening, it is going to start running all the side effects that we have inside. So this may seem like a problem, but fortunately, Combine also offers a way of converting any eagerly evaluated publisher into a lazily evaluated one. And we can use the deferred publisher that takes a closure, returning a new publisher, and makes it lazy. Okay, so we had the eagerly evaluated future, so we wrap it into a deferred publisher, and now everything is lazy. So now, whenever we invoke the third version of our greeting function, we are not going to see anything printed into the standard output. We will just have a publisher where we can start chaining combinators like map or flat map, and we will be able to work with all these things. And then in the edge of our program, we will need to call sync and pass a closure here to subscribe to this publisher. And actually, when we sync into this publisher is when all side effects will be evaluated. So at this point, you may be wondering, well, why does it matter? Because in the end, I'm going to be running side effects. So why does it matter if I postpone them instead of running them at the moment? Well, we're going to illustrate this with a quiz. So consider this short piece of code. We are using the second version of our greeting function, which is the eagerly evaluated one. Okay, so we have a call to this function, and then we flat map and call the greeting function again. So how many times do you think this code will print hello to Swift community?
Well, I would say since it's eagerly evaluated, so when greet returns, the side effect will be run a first time. Then flat map is run one time because the promise was called with one success value, which was void, so the empty tuple. So then greet you is called another time, and it does the same thing. So I would say it gets printed twice on the console.
Correct. So we are evaluating this function, and then we flat map, and as this one was successful, then we are evaluating this second one. So we will see the message printed twice. Now we are going to perform a small refactoring. As we are calling twice to this function, we may say, okay, let's extract this into an intermediate variable, and we can replace both calls by the result of calling this function. Okay, so now This seems like a harmless refactoring, but how many times do you think the message is going to be printed?
This one is a little bit more like difficult, especially since I'm not like that familiar with combine. So the question is basically like, yeah, is the side effect going to be run only once, or is it going to be repeated? So, I mean, if we try to reason about it, so publisher is going to be run, then we flat map and we say we want to return the same publisher, but it's the same instance because it's a reference type and it has already been run. So I would say only once, but I'm not sure at all.
Yeah, exactly. It is going to be printed only once because we have said that this publisher, the one that we are returning from the second version of our greeting function, is evaluating side effects eagerly. So whenever we get this, it is already completed. So side effects have been run, and we will only focus on the provided value, which is the void value, okay? So here we will see the message printed once, and then this is like doing nothing. So this harmless refactoring makes our code behave differently, okay? And this is because eager evaluation of side effects breaks something called referential transparency. So referential transparency is something that you are going to see a lot of times as soon as you start reading about functional programming. And it is something very simple. It is a property of our code by which we can replace parts of our program by its evaluated value, and the behavior of the program doesn't change. Okay, so in this case, we can see that this property, referential transparency, is not satisfied because we have replaced parts of our program by its evaluated value, but the behavior of the program changed. In this case, we were seeing 2 messages printed into the standard output, and in this case, we are only seeing it once. Okay.
And so I'm thinking, so the function greet2, if we try to think on it in the terms that you said earlier, so for instance, would we say it is a pure or an impure function? Basically, it's an impure function, if I'm right.
Exactly, it's an impure function because it is running side effects, not only providing a return value, but actually running side effects. So let's see what happens with our third option, the lazily evaluated one. So in this case, it shouldn't surprise us that the message is printed twice because it should behave exactly as the first case that we have analyzed here. Good, so now, what happens if we extract the publisher 2 as the result of calling our lazily evaluated version of our greeting function, and we replace both calls by their actual result?
Okay, so this time, so greet3, it's lazy, so nothing is happening until someone has started to listen. So basically until sync has been called. So I would say that this time it should behave the same way, meaning that so when we start to listen, publisher 2 is going to be run, its default block is going to be run, it's going to print to the console, and then the default block should be run again in flat map, and it should print in the console also.
Correctly. So this is going to be, as soon as we start listening into this publisher, we will run side effects and it will complete. And whenever we flat map and start listening again to this second publisher, side effects will be run again. So now, thanks to this function being pure, because of the lazy evaluation of side effects, we have referential transparency in this piece of code. We are able to extract a piece of code and replace all its occurrences by its evaluated value, and the program will behave exactly as we expect. So these are the 3 properties that we must have if we want to write functional programming.
Yeah, and I think maybe it shows us something interesting is that, you know, sometimes when you read about functional programming, a definition that you often see, and we've seen now it's a bit incorrect, as people say functional programming is about programming without side effects, but actually it's about effectively managing side effects, we could say.
Exactly. So with this, we are able to encapsulate side effects as data, work with them as we work with other data, just as we work with arrays or results or whatever, because we have proven to be very good at managing data, but not so good at managing side effects. So if we make side effects as data, we can leverage all these techniques that we have been refining through the years and making our code easier to handle. So with this, this is everything you need to know about functional programming. As long as you are writing functions that are total, deterministic, and pure, you're practicing functional programming. And notice that this is not incompatible with object-oriented programming or any other paradigm. You could be doing both at the same time. As long as you're writing methods that are total, deterministic, and pure, you're practicing functional programming.